we search for the eigenvalues and the eigenvectors of a 3 by 3 matrix. Then a matrix which represents a linear endomorphism of R3 into R3, and it will associate the vector of components x, y, z, the v vector in R3, to the vector. After the transformation, we will go to x plus y in the first row minus 2x minus y in the second, and to z in the third row. This will be the vector w after the transformation. As usual, we begin by searching for the eigenvalues. Eigenvalues solve the determinant of lambda I minus a equal to 0, that is the characteristic equation. Then we will have the determinant of lambda minus 2 minus 1, 0 in the first row, 2 lambda plus 1, 0 in the second row, and 0, 0 lambda minus 2 in the third row. This calculation has to get 0. Of course, I will search for the determinant. I will use the definition of determinant and calculate it starting from the last row, because it contains 2 zeros. Then the calculation will be simple, and then the determinant becomes lambda minus 2 times the determinant of the matrix you obtain removing the third row and the third column. Then we have the determinant of lambda minus 2 minus 1 to lambda plus 1. This has to be equal to 0. We have lambda minus 2 multiplied by the determinant of the 2 by 2 can be simply obtained, lambda minus 2 times lambda plus 1, and then we add 2. We obtain lambda minus 2 times, inside the square brackets, we have lambda square plus lambda minus 2 lambda minus 2 plus 2. We have a cancellation of 2 with minus 2, and we may factorize also lambda. Finally, we obtain lambda times lambda minus 1 times lambda minus 2. Therefore, we have 3 eigenvalues. We have a first eigenvalue, lambda 1, which is 0, a second root, lambda 2, which is 1, and a third root, lambda 3 plus 2. We have a case of 3 real and distinct eigenvalues. And now let's deduce and possibly represent, since we are in a case of real eigenvalues, the corresponding eigenvectors. They solve the problem AV equal lambda V, where only 2 rows out of 3 have to be written, because this system is a homogeneous singular system. It's run by a 0 determinant. Well, we cannot assume that the 2 rows to be kept in the calculation are the first 2. We will see case by case which is the row that has to be cancelled. Let's find the eigenvectors associated to the first eigenvalue lambda 1. They will solve AV equal 0 times V, 2 rows only. Well, AV is 2x plus y equal 0, first row, second row, minus 2x minus y equal 0, third row, 2z equal 0. This is the system. And it immediately gives you that the third component has to be 0. From the first row, I deduce y equal minus 2x, but of course the second row is multiple of the first one and can be cancelled. Then a representative eigenvector associated to the first eigenvalue is a vector where the third component will be 0 and the second component is minus twice the first component. This is the eigenvector associated to lambda 1. And now I search for the eigenvectors associated to the problem AV equal to 1v, since 1 is the second eigenvalue. We will have 2x plus y equal to 1 times x in the first row. In the second row, minus 2x minus y equal to 1y, and in the third row 2z equal 1z. And out of 3, only 2 rows have to be kept in the calculation. We deduce that from the last condition z is 0. The first row becomes x plus y equal to 0. The second row becomes minus 2x minus 2y equal to 0. Then we immediately see that it is the second row that has to be cancelled out of the calculation. And we obtain a representative eigenvector with a 0/3 component and the first 2 components which may be added to get 0. Then, for instance, I can keep minus 1, 1, 0 as a representative eigenvector for lambda 2. And finally, concerning the third eigenvalue, we have to solve the system AV equal to 2v, and we will keep only 2 rows out of 3. The system gives in the left-hand side, we have 2x plus y minus 2x minus y and 2z. This system has to be put equal to 2v. Then I have 2x in the first row, 2y in the second row, and 2z in the third row. We see immediately that now it is the third row that has to be cancelled because it is an identity, and from the first 2 conditions we deduce immediately that the first is solved when y is equal to 0 after the cancellation of x, and if y is equal to 0 from the second we have x equal to 0. No condition on z. Remark that if a variable is not constrained, this variable is free. Then the eigenvector associated to lambda 3 has to be a non-trivial eigenvector and has 0 first component, 0 second component, and free last component. The last component is free, and that as a representative I pick the value 1. We have obtained 3 eigenvectors, and you see that none of them is multiple of the others. Eigenvectors, indeed, corresponding to different eigenvalues, are linearly independent. Let's end the exercise representing them. I have the space R3. I am going to represent the 3 eigenspaces. The eigenvector corresponding to lambda 1 shifts of 1 unit in the direction of the first component, if that is the x component. And then I will have to shift minus 2 units in the y direction, then move negatively of 2 units toward the left. The vector will be more or less this one. And what about the eigenvector of the second eigenvalue? Well, here I have minus 1, 1 to be represented. Then in x I will move negatively in the direction x and positively 1 in the direction y to get this vector. And about z, the third eigenvector will have 0x 0y component and only 1 in the z direction, then vertically shifting. We have had the 3 eigenspaces. The eigenspaces are the 3 straight lines corresponding to 3 eigenvectors, then to the blue, the green, and the orange straight line, which are the 3 eigenspaces. Indeed, we have 3 regular eigenvalues, because every eigenvalue is simple, it has algebraic multiplicity 1, and geometric multiplicity equal to 1. The geometric multiplicity is the dimension of the associated eigenspace.